Okay, so here we have a 4-bit synchronous counter with a parallel load. So a 4-bit synchronous counter, we can expect that it does, unless you are told otherwise, is that it counts and that it counts correctly. And so when you look at the outputs, you have the outputs Q0, Q1, Q2, Q3, and here I am writing them in the correct order with the least significant bit here at the right. That when you run this counter, if it's allowed to just go on each clock cycle, it will count up by 1. So if it starts at 0, 0, 0, 0, the next clock cycle you would expect to get 0, 0, 0, 1, and then 0, 0, 1, 0, and then 0, 0, 1, 1, and then 0, 1, 0, 0. So you can expect it to count. And then when it gets all the way to 1, 1, 1, 1, you would expect it to go back to 0, 0, 0, 0. So you are given this counter and you are allowed to believe that it works. But you can load things and you can use this load to make it do something different. So this one says, what is the first count after a load signal? So when it gets a load signal, then it loads the values that are here on our Ds. And so then on load, what we get, so we have our 0-bit, so Q0, Q1, Q2, Q3. Q0 will be 0, Q1 will be 0, Q2 will be 0, and Q3 will be 1. So the first count after the load signal, we said we expect our counter to count correctly, so we would expect our next count to be 1, 0, 0, 1. So that's what we would expect, the first count after the load signal. Now, it says, what is the last count before a load happens? Well, let's see what makes a load happen. What makes a load happen is we have the AND of Q1 and Q3. So a load will happen if you have the AND of Q1 and Q3. So let's look at what that would look like. So Q3, Q2, Q1, Q0. When will the AND of Q1 and Q3 be 1? When they are both 1. So the first time both of these are 1, that would signal a load. So let's continue counting. So the next count after this would be 1, 0, 1, 0, and that is it. That's the very next one. This will be the last count before a load happens, because now Q3 and Q1 are both 1. Okay, and then for part B, we're supposed to use a 4-bit synchronous counter with a parallel load, and a minimum number of additional gates is needed to construct a counter that counts from 0, 1, 1, 1 through 1, 1, 1, 0. Okay, so we'll have an enable D0, D1, D2, D3, load, a clock, and Q0, Q1, Q2, Q3. And you also have something here, an output carry, and that can be used to link two of these counters together. So this is a 4-bit counter. If you wanted to have an 8-bit counter, you can use that carry bit to link the two together. But we want to start at 0, 1, 1, 1. Now, do pay attention to, this is Q0, Q1, Q2, Q3. So Q3 would be 0, and these would all be 1. And we want it to count through to 1, 1, 1, 0. So a lot of times what will work, well, what will always work would be if I take the AND of all of these, and this is Q3, Q2, Q1, Q0, and I make Q0 0, and the other's 1, that will always work to be your load. But a lot of times you don't need the 0 parts. Sometimes you do, but a lot of times if we think about what would happen with counting here, we start with 0, 1, 1, 1, and we want it to go through 1, 1, 1, 0. So the next count would be 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. That's where I'm trying to get to. So at any point between where I started and where I wanted to end, was there any other time where all three of these were ones? No. So that means I didn't need to put that 0 in here. I could have, but it, you know, it's just extra. It might cost a little extra. You don't have to have it. No, I think they'd like it better to be more efficient. If you're not 100% sure, then I would put it in. Okay. Next. How long have we been sitting here?